Lesson 2 is on ratio, and ratio is the second of 10 major topics we'll be reviewing in these first 20 lessons. And that's also a difference. If you did Shormann pre-calculus or another course, then typically the quarters had 25 lessons, but Shormann calculus has 20 lessons per quarter. And we're covering ratio even though this is a calculus course because there are applications of ratio everywhere in calculus. And we're also just trying to think of general versus particular, abstract versus concrete, ideas versus real situations. So just think about some of the ideas in G.K. Chesterton's quote here that he said, an impersonal force might be leading you to a wilderness like the one above in Katmai National Park, a wilderness of perfect flatness or a peak of perfect height. But only a personal God can possibly be leading you, if indeed you are being led, to a city with just streets and architectural proportions, a city in which each of you can contribute exactly the right amount of your own color to the many-colored coat of Joseph. So in figuring out that place of yours in God's creation and that purpose that he put you in, there's colors in Joseph's coat. They all matter. You matter. You're one of those colors. And so part A, we're looking at ideas in math like ratio and proportion, and ideas in your world, the Christian adventure, and just how proportion relates to that. You understand what proportion and ratio, things like that, mean in other places. It's going to make the math meanings of it just easier to comprehend and to get a hold of and connect to the rest of your world. So this word ratio that we're talking about here, the title of this second of 10 major topics in Shormann math, has its origins in the idea of rational, which means reasonable thought or purposeful study. So the Greek word for this is logos, and that also means word. So for example, John 1:1, it says, in the beginning was the Word, and the Word was with God, and the Word was God. Original Greek manuscripts, they use logos in place of word. So think about logos as word. Logos is also found in words like biology. That logi part there. Bio is life, logi is study of. Also consider the word logic. When someone says that's logical or that makes sense, they're talking about the same thing. Or that sounds reasonable, they're talking about something being logical. So we can also compare John 1:1 to Proverbs 1:7, and that says, the fear of the Lord is the beginning of knowledge, but fools despise wisdom and instruction. And we can learn from that if you reject logos, in other words, God's word, you're rejecting God. That means you are rejecting reason. But some things in life just aren't reasonable, like love, irrational numbers, so on. And that's why wisdom and instruction are important too. And just a side note here, in this part A, there's no math in it, but just some ideas, some things to think about. I may ask you questions about part A in the practice sets, so you might just want to refer back to the reading assignment for those. Feel free to take any notes on key ideas that you see in this as well. So we can use this idea of ratio as a tool to study God's creation by comparing this to that. That's what we're doing when we think about ratio, whether mathematically or otherwise. We're comparing one thing to another. So ratios help us make sense of how one thing relates to another, including how the Creator relates to His creation. And we're comparing numerical amounts usually in math. Fractions. Think about fractions. What is a fraction? It's a way to numerically describe a ratio or proportion. It can also be thought of as portions. And actually the word fract, where that came from, it was first used by Christians in churches as a way to describe the breaking of the bread during Holy Communion. So this idea of ratio is everywhere. And why is that? Well, it's because God's hand is everywhere present, as He uses every way He can to turn us towards Him. As Leonard Euler famously said, and this would be a good thing to make a note of, calculus is concerned with ratio. So Leonard Euler, the most famous mathematician in the history of everything, he said that calculus is basically about ratio, comparing this to that. If he thinks that's what it was about, then probably be a good idea if we considered it that way as well. Throughout history, humans have recognized that proportion and equality of ratios, that's what proportion is, 1/2 equals 2/4, things like that. That's an idea expressed in a variety of seemingly unconnected ways. And William Priestley, a 20th century math professor, he wrote in this book, Calculus, a Liberal Art, he wrote this here: the notion of proportion and equality of ratios, it manifests itself in mathematics as measurement, in rhetoric as analogy, and in music as harmony. So measurement, analogy, harmony. Proportion is, of course, closely tied to beauty in all the classical arts. So again, as you can see, this idea of equal ratios, it's much more than a math concept. And that's what we would expect, though, in a world created by a God who is both one and many, with whom relationship matters. How does this relate to that? So when we think proportion, we're thinking relationally. That means seeing obvious differences between things, but also seeing how they relate. So many times the world seeks to only explain the differences between things, and government education systems sometimes they seek to train students to separate facts and opinions. They treat facts as things that can be tested and proven, opinions as beliefs held by individuals and not necessarily true. But not all facts can be proven, like Euclid's axioms and postulates, that we call those self-evident truths that we'll talk about in lesson 7. And also, it's perfectly reasonable to believe in a fact. It's like saying most cardinals are red is a fact, but I can believe that that's true also, right? God's word says if I surrender my life to Jesus Christ, I'll be saved and redeemed. It's a fact that the Bible says that. I can believe that fact also. So, while obviously there's differences between facts and opinions, we should also see how they relate. And that brings us back to proportion. This idea of proportion, that should encourage us to find the real harmony that exists between things like facts and opinion. Proportion that also helps us to see the inherent design in the world, helping us make that common sense connection between the Creator and His creation. One more thought on proportion before we continue on here. As a human designed in God's image, you're filled with incredible purpose for this world and eternity. That's kind of what G.K. Chesterton was pointing at in that quote. So committing to that idea that you do have an incredible purpose that might help you as you spend time in this math course or elsewhere, and making that time more fun for you. If you think of it not as a horrible chore to trudge through with much complaining, the biblical way to think of it is an adventure. James chapter 1, 2, and 3, consider it pure joy when we face trials. Quoting G.K. Chesterton again in his book Orthodoxy, man must have just enough faith in himself to have adventures and just enough doubt of himself to enjoy them. So some confidence there that yes, I can do calculus, but also just enough doubt so that when you come across a problem that you finally get right, you're not like, oh yeah, I knew I'd get that eventually, but yes, I figured something new out, all right, and you have some joy in that. Well, moving on to part B on rational and irrational numbers, look at this chart here and notice how the real numbers, those can be broken into the rational and the irrational numbers, those two groups. Real numbers are anything that can be written as a fraction of integers, that's the rational numbers, along with all the numbers that can't be written that way. Those are the irrational, the unreasonable numbers, the ones that totally freaked out the Pythagoreans. So irrational numbers like pi, those can be written as decimal numbers, just so we have to round them to put them on paper because their decimal pattern does not repeat. It's not like pi is 3.141414 repeating and putting a bar over the 1/4 part to show that it's repeating. No, it's like this. Erase that. And it's just 3.14, and then those decimals, there's no repeating pattern there. Some people define pi as 22/7, a ratio of integers, a fraction of integers, but that's a simplified version of pi, just like 3.14 is. That's not really true pi. So be familiar with that diagram and what the real numbers are and how those group together, and the irrational on the other side. And it's not like there's just 4 of them or something. Those are just examples of irrational numbers. Pi square root 2 phi e, Euler's number. So speaking about some of those irrational numbers listed in the chart, we'll call those special irrational numbers, and a lot of times they're found in nature, and those include phi, pi, and e. And note also, while any 2 numbers, they can be written as a ratio, that doesn't mean they are rational numbers. So for the 3 numbers we're going to talk about here, the comparison of this to that results in an irrational number. So first up, we'll talk about phi. That's also called the divine proportion, the golden ratio, or the extreme and mean ratio. And Euclid, he talked about that a long time ago, 2,000 plus years ago, and he showed that phi can be found from the following proportion of line segments, where the larger segment, AC, to CB, that ratio is the same as AB, the whole segment, to the larger AC. So the whole thing, comparing that to the larger piece that it's broken into, that's proportional to the larger piece it's broken into to the smaller piece. Rounded, phi equals 1.618. Interestingly, 1 over phi, that equals 0.618. I'm rounding this because it's irrational. It actually goes on forever in a non-repeating fashion. Guess what? Phi squared equals phi times phi. That's 2.618. It shows up in many natural phenomena, like the pattern of a chambered nautilus, the pattern of seeds on a composite flower, the random-looking pattern on a dragonfly wing. A lot of different places it appears. So hopefully these are reviewed to you, but just looking at pi again, that is an irrational number. It equals the ratio of the circumference to the diameter of a circle. And normally in this course, and make a note of this, 3.14 is what we use for pi in this course. And that way everybody kind of gets the same answer. You're not thinking, well, should I round to this? Should I use the pi button on my calculator? How do I deal with pi? And E, next, that's the natural number, also called Euler's number, after Leonhard Euler. Rounded, that equals 2.718. And again, that's normally what we'll use in this course. So one way to estimate its value, it's by adding the values of the following infinite series. You just do 1 plus 1 over 1 plus 1 over 1 times 2 plus 1 over 1 times 2 times 3 plus, I bet you can figure out what you would do next, 1 over 1 times 2 times 3 times 4, and so on. The more of those you add up in that type of pattern there, the closer you'll get to the actual value of E. Pi has all kinds of important uses. Anything related to a circle or a circular pattern, a repeating periodic pattern, it'll relate back to pi. E has lots of important uses too. So calculating bacteria growth rates, it helps with that. Calculating future values of a present sum of money in a savings account, things like that. So let's take a look at an example now, example 2.1. Be familiar enough with rational, irrational numbers, the differences between them, to answer questions like this. Which of the following here is an irrational number? Which of the following would have a non-repeating pattern of decimals? Well, just looking at that, we have square root of 2, square root of 4. Well, square root of 4 is 2, right? That's an integer. I is an imaginary number, so it's not even in that group. 0 is another integer, so that doesn't count. It's a square root of 2. If you didn't know it was a square root of 2, then you could figure that out by process of elimination. And you could also do square root of 2 on your calculator. You'll see it's like a 1.414 non-repeating kind of thing regarding the decimals. So continuing on with ratio and our review here, to simplify complex fractions, that's what we're going to focus on, is not just any fraction, but complex fractions. Turn them into a multiplication problem, multiplying above and below by the reciprocal of the denominator. And notice there's three things to remember here. Doing that, remembering that anything can be written as a fraction by writing it over 1. And then 3, fractions are in standard form when there are no radical signs or imaginary numbers in the denominator. So remember that too. So looking at example 2.2, simplifying those fractions there. For a, we can turn that into a multiplication problem by multiplying above and below by the reciprocal of the denominator. You can see the denominator is 4 over x, so we multiply above and below by x over 4, the reciprocal of the denominator. So then we end up with 2 times x is 2x over b times 4, we just say 4b, and all of that over 1, because that's what this will equal right there. But it's understood that there's a 1 there, so we don't write that. We're trying to simplify this, so when we do times 1 over 1, we don't put the 1 on that. And then 2 over 4, that's the same thing as 1 over 2, right? So we're not going to write 1x over 2, we just write x. It's understood there's a 1 in front of it. X over 2b. That's the simplified form of that fraction. Look at b. X over square root of 5, that's in the numerator, and then over k. Thinking of 2 above, anything can be written as a fraction by writing it over 1. We could do that with the k, right? We could say k over 1, and now we see a fraction over a fraction, which means we could multiply above and below by 1 over k. 1 over k. Cancel all that out, and we get x over the square root of 5k. Now wait, we're not done. What does 3 say above? Fractions are in standard form when there's no radical sign in the denominator. So we need to multiply above and below by the square root of 5. So then we get square root 5x over 5k. And c, 1 over 5 minus 2i, well, that's a complex number on the bottom. We're looking at 3 again. You can't have imaginary numbers. That's not standard form. It's okay to do that, but it's just not standard form. Our goal here is to get these in standard form. So we multiply above and below by the complex conjugate. So we have 1 over 5 minus 2i. I'll just put that in parentheses for right now. We want to multiply above and below then by the conjugate. 5 plus 2i over 5 plus 2i. Why is it okay to multiply above and below by the same thing? Well, because that equals 1, right? 2 over 2 equals 1. 5 over 5 equals 1. 5 plus 2i over 5 plus 2i equals 1. We're just multiplying by 1 is what we're doing. We're not changing the solution here or the numerical value of this. We're just changing the way it looks. And that's a key idea that hopefully you remember way back from Algebra 1. 5 plus 2i on top, and then just let's mentally do the denominator. There'd be a 5 squared, and then you get a plus or minus 10i, which cancels out. That's why we multiply by the complex conjugate. And then we'd have a minus 2i squared, which is minus 2 times negative 1, or minus 4 times negative 1, plus 4. So we have a 25 plus 4 is 29. And so writing this in a plus bi format, we'd have 5 over 29 plus 2 over 29i. Right there. Moving on to part D on logarithms or ratio numbers. That's what that means. Logarithm means exponent. Also, that's the most important thing. Logarithm means exponent. So remembering the connection between logarithms and exponents, that is the single most important thing for easily understanding logarithms. And originally, though, the logarithm, it was Greek for ratio number of ratios. And John Napier, he invented logarithms around 1614. And you can read more about him and the history of logarithms in the review lessons. that are in your reading assignment and on the e-learning campus. But here we're going to focus on just solving logarithm problems without a calculator. The assumption here is that you are fairly familiar with those, so you might want to make a brief review in your reading assignment looking at the rules and definitions. But let's look at this example 2.3. Which of the following here must be true? So in number 1, we can apply the quotient rule for logarithms to figure that one out, right? So log 100 minus log 10 is the same thing as saying log 100 over 10, which is log 10, not log 1000. So that one doesn't work. The next one there, log of 1 equals 0. Doesn't matter what the base is, that's always true. Log of 1 equals 0. Log base 5, log base 10, natural number, whichever. Number 3, log base 4 of the cube root of 4. Well, one thing we could do here is think about the power rule for logarithms and rewrite that as log base 4 to the 1/3 power. And applying the power rule, we have 1/3 log base 4 of 4. Log base same of same is 1. So this just equals 1/3. So in other words, that's false. That doesn't work. It's not 4/3, it's 1/3. So the only one that works there is number 2. So that means choice B is correct. Moving on to part E now, on rate and ratio word problems. The first thing to notice about the word rate is its similarity to the word ratio. You'll save yourself a lot of confusion if you simply remember that when you see the word rate, think fraction. Rate is a specific type of ratio, so where usually you have two measurements you're comparing. And I mean, just think of speed. If you drove 60 miles in 1 hour, your average speed would be 60 miles divided by 1 hour, or 60 miles per hour, which we also say is mph for the units on that, but it means 60 miles over 1 hour. It's just, we don't usually write it like that as a fraction. We don't say 60 miles over 1 hour. We abbreviate that to 60 mph, but it is a fraction. So rate, it's normally associated with speed, like we just described there, and we'll study that a lot in calculus. And rate can really be for comparing any pair of measurements, so miles per gallon, dollars per quart, and so on. If you understand ratio, then you can understand rate, which means you can understand calculus too. And we'll have some review of that, lessons 20 through 22. After all, calculus, it's just about studying rates of change, like we mentioned earlier. So look at example 2.4, and let's read this through. As it rotated, the tidal turbine's blade tip traveled through its 45-meter circumference in 5.98 seconds. Calculate the turbine blade's tip speed rounded to 1 decimal place. So we have this turbine, maybe some kind of propeller shape here, and I mean, just think about it. It's going to rotate through a circular pattern, right? That's why we talk about its circumference. And so that is 45 meters. So it goes that whole distance in 5.98 seconds. Speed is a distance traveled over time. So we can figure out the speed at that tip of the blade just by doing 45.0 divided by 5.98, and that's 7.5 rounded to 1 decimal place, 7.5, and we'll say MPS, meters per second. So do that on your calculator, 45 divided by 5.98, and you get like 7, rounding to or having more decimal places than just 1. It's like 7.53. And just something to remember here, if the remaining places, like if you're rounding to 1 decimal place, then and that 1 place is a 5, if the remaining places are 5 or greater, then round up. So we would say 7.6. This is less than that, so it's 7.53, round just to 5. So it didn't say this, but if it had said 7.55 there, we would have rounded to 1 decimal place as 7.6. Look at example 2.5 Brand A peaches cost $11.99 for 24 peaches. Brand B cost $6.49 for 12 peaches. Which brand is the better deal? In other words, which one is the lower cost per peach? So we can't just look at the prices there and think, oh, well, brand B is cheaper because it's $6.49. Well, no. How many peaches are we talking about here? What's the cost for each peach? That's what we mean by better deal. What's the lower cost per item? So for brand A, we have $11.99 divided by 24. Get your calculator out. That's 49.96 cents. So to get that in cents instead of dollars, you could just type in on your calculator like this, $11.99, 1,199 cents instead of $11.99 divided by 24, 49.96. We round up there and to 96 cents. And then for brand B, we have $6.49, or we could just say 649 cents divided by 12 peaches. That equals 54.08 cents per peach. So because brand A is a lower cost per peach, we'd say that that's the better deal. Last, let's look at similarity and scaling, and some of this will be mathematical, some won't, but that's how proportion is, right? And since mathematics is a language of science, science is about observing God's creation. It makes sense that using realistic examples is often helpful in understanding math's abstract nature. So mathematicians, they sometimes say, I will use a concrete example to describe this abstract concept. And so of course they don't mean like material that you make a road out of or whatever. They don't mean that kind of concrete. It just means something real or actual. So when you see that word used in a math sense, that's what that means. A real thing compared to just an idea, a general idea, an abstract thing. So we can connect those two things sometimes using an analogy. And in rhetoric, the word analogy, that's used to describe how one thing compares to another seemingly unrelated idea. So for example, we're making an analogy when we show that mathematical ideas relate to reality as abstract relates to concrete. And we can write this in an Aristotle type form like this. Ideas to reality as abstract is to concrete. Ideas are to reality as abstract is to concrete. So where ideas and abstract things are similar and reality and concrete are similar. Jesus' parables, like Matthew 25, for example, and the parable of the talents, that is an analogy. The kingdom of heaven is to a Christian as a Lord's possessions are to his servants. Something to be treated wisely and carefully and with much care. So moving on now from analogy to proportion, and why are we studying analogy? Why did we just study that and rhetoric? Well, as we've mentioned, analogy is to rhetoric what proportion is to mathematics. Analogy is to rhetoric what proportion is to mathematics. I just made an analogy about analogies. So we say this is proportional to that if they have equal ratios, right? This is proportional to that if they have equal ratios. So for example, you know, like 4/8 equals 1/2. They both equal decimal form 0.5. We could write that like an analogy. 4 is to 8 as 1 is to 2. Reducing a fraction like 4/8, that requires you to think 4 is to 8 as what is to what. You have to think about it like an analogy. And you divide above and below by the greatest common factor of 4 to get it into that more simplified form. And you could also multiply above and below by 1/4, the reciprocal of 4. So there's another way to do it. So doing it like that, if you think of 4 over 8, think of it like a fraction. You multiply above and below by the same thing. We're creating a proportional or similar fraction. And that fraction that we multiplied by, the 1/4, oftentimes that's called the scale factor. If you've ever built a toy model, you may have noticed on the box that it said like this is a 1/20th scale or a 1/40th scale or something like that. So in order to make the model proportional to the original object, every model piece, that must be reduced by the same scale factor. Maps are also this way. And so are photos, like the one at the beginning. If this photo wasn't proportional to the actual mountains and the actual people and airplane, it would be out of proportion, and you probably notice. So let's finish up here in part F and look at example 2.6 with an analogy. Which of the following is an incorrect analogy? So let's just read these, think them through. A building height to the height of 1 story is like Joseph's coat of many colors to the color blue. So what's the idea here? It's like the one piece of a larger piece, right? So one piece of a larger puzzle. So both sides describe that, so that one's okay. And then B, 4 is to 8 as 2 is to 4. Well, they're both equal to 1/2, right? So that one's okay. C, chicks are to hens as fawns are to doe. That would make that true. So either that or the hen side is wrong. I mean, you can't tell which side is wrong here. It could be that it should be chicks are to some other random vegetable or fruit. So that one doesn't seem like that's the right one, but we'll just look at the next one too. 100 to 10. 100 over 10 is just 10. 20 over 2, that's 10 also. That one's okay, so it is choice C, is the incorrect analogy there. Last one, example 2.7. The model whale was a 1/25th scale replica. If the actual whale was 50 feet long, how long was the model? So think of this like way back, maybe probably pre-algebra. Fraction of whole equals what? So sometimes it's thought of as F times of equals is. So the fraction here is 1/25th times 1/25th of 50 feet is, well, 50 over 25 is 2. So put units on it too, 2 feet. That's what the model whale would be, 2 feet long. And that is all for lesson 2.